In this session, we will discuss about the Verilog code for ripple carry adder. As I told you earlier, ripple carry adder is a combination of or a collection of full adders based on the number of bits it is required. If it is an 8-bit ripple carry adder, it will have the combination of 8 full adders. 5-bit ripple carry adder means it will have a 5 full adders. Okay. Now full adder. What is full adder? It is going to add 2 input bits and the carry generated in the previous stage. So that is reference to full adder. If I assume A and B are the 2 input bits and the C in is the carry generated in the previous stage. So as we consider the 3 input bits, definitely we will have 8 combinations. So when you add in a binary addition, 0 plus 0 is 0 and 0 plus 1 is 1. When you add 2 1 bits, the answer is going to be 2. So what is the binary equivalent for 2? 1 0. In that case, 0 is an sum and 1 is a carry. So when I consider this case, 0 1 1 1, the sum is going to be 0 and the carry is 1. When you consider this triple 1, this is going to be a 3. And what is the binary equivalent for 3? This is 1 1. In that this 1 is a sum and the other one is a carry. So when I am going to describe this full adder as a circuit, what are the gates involved in it? So to find out it, I am going to express this as an equation. This equation can be derived using a Karnaugh map in the simplified form. So how will you create this Karnaugh map? Wherever you have 1 in this truth table, that will be tabulated in the Karnaugh map. By applying this simplification rule, I have got the sum equation as A XOR B C. Whereas when I consider the values of 1 in the carry and when I tabulating it in the Karnaugh map, it gives the answer AB plus BC plus AC. From these expressions, we have identified that to implement the sum, I need 2 XOR. To implement the carry, I need 3 this logical OR gate is required as well as a logical AND gate is required. So to represent this, I am going for this circuit. So what are the inputs? A, B, C in are the inputs. What are my outputs? Sum and carry of the outputs. So to represent this, A and B are first XOR and that will be XOR with the third input bit and so on. So this is the construction of our full adder circuit. Okay. In the Verilog code, how we are going to describe this hardware, that we'll see now. So this is our circuit. So for assumption, I have taken this X, Y, Z are the inputs. Okay. So in that, so whatever is displayed in this blue color is indicating the fundamental blocks or the keywords, sorry not blocks, it is the keywords used in the Verilog code words. In that, the very important thing is a module. Module is indicating, it is describing the functional unit of the circuit and what are its inputs, it is a list of inputs and what are its outputs. And within this body of the module, we will have the functional description about the circuit. Okay. So, from this, what are the inputs? X, Y, Z are the inputs. That is referred by the keyword input. And then sum and carry, S and C not are my outputs. That is described by the keywords output. But intermediate, when you observe the circuit, we have some 3 intermediate results, T1, T2 and T3. These are not the final outputs. So that will be stored with the temporary variables. Apart from input and output, you have the temporary variables. These temporary variables are represented by the term called as a wire. Wire is a temporary variable. So in this equation, in this circuit, totally we require 3 intermediate values. So therefore, this wire T1, T2, T3. Okay. Now we will see that. As I told, this Verilog code can be written using 3 types of modeling. This coding has been written using a structural or gate level modeling. That means the description is explicitly representing the name of the gates. So XOR gate. Totally how many XOR gates are used? 2 XOR gates are used. Therefore XOR and I naming those gates are G1 and G2. The first one G1. For this I am naming this is G1. For this G1 what are my inputs? X and Y are the inputs and the output is T1. Therefore, I have taken this is my output and the X and Y are the inputs. For the second XOR gate, what is the final output? S is the output and the inputs are this T1 and the Therefore, T1 comma Z. Now, when you are coming to the next one, AND gate I am going to use. How many AND gates we have used? 2 AND gates. Therefore, let me name this is an AND gate, and already I have named this G1 and G2. Therefore, G3 and G4 I have used. And what are the inputs for the gates G3? This T1 and Z. T1 and Z it is going to give this one, this T3, and this is going to generate my T2. And after that, these temporary variables are added together to generate my final output, that is my carry. So these all are encapsulated within this module. This is our function unit. It is indicating the function relationship between the inputs and the outputs, and the gates involved. Everything is all described. So this module is indicating the functional relationship among the inputs and the outputs, and what are the gates are involved in it, and then how these values are interconnected, how the values are propagated. All are clearly explained in this module, and this is ending with the keyword end module. So this is a HDL or Verilog code for a full adder. But our objective is creating a ripple carry adder. So let me take an example of 8-bit ripple carry adder. That means totally I have 8 full adder circuits. 8 full adder circuits are there. So each full adder will have 2 input bits and it will generate 2 output bits, sum and carry. So let me explain. This is A0 to A7 and B0 to B7. These are my 2 inputs. Therefore, definitely the output is also will be from 0 to the sum of sum. If I am naming it as a sum, and that will also be an 8-bit number. So if a sum of 0 to sum of 7 is there, and then carry. The carry is finally what is carry generated in the this one most significant bit. The intermediates will be carried and it is added in the next one. So you observe the circuit carry is. While adding the lower 2 bits, there will not be any carry. Therefore, the Cin is taken as 0. And it is generating one carry, and I am naming it as a C of 0. That is forwarded here. Therefore, what are the inputs here? A1, B1 and the C of 0. So it produces an output sum of 1. And what is the carry associated with this? C of 1 is a carry. Likewise, the carry is propagated, and the carry propagated generated finally from the MSB adder. That is our final carry of the circuit. Okay. So let me explain the hardware description language. How we are applying this GDL. How we are writing the Verilog code for this ripple carry adder circuit. See, while explaining this, I am going to tell a very important thing called instantiation. Now we will see how to write a Verilog code for a ripple carry adder. In this, the very important concept we have is an instantiation. What is meant by this instantiation? In the ripple carry adder circuit, we have 8 full adder. So to reduce the code and to reduce the space occupied by the code, we are going to use our instantiation. So what is meant by this? This is a full adder circuit. This is our HDL language for our full adder circuit, and this is referred as one instance. This full adder is going to be used 8 times in our main circuit. Sorry, not main circuit, main program. So in the main program, this instance will be called 8 times. This process is referred as an instantiation. So this is known as an instance, and this instance will be called 8 times in the main program. So that is known as an instantiation. If it is of a 5-bit ripple carry adder, this will be called 5 times in the main program. So this is the concept of instantiation. Now we will see the code for it. The another important thumb rule is whatever the variables we used in the basic instance should not be repeated in the main program, main module. So in this full adder, in the basic module, I have taken X, Y, Z are my inputs, and the S and C not my sum and carry. So in the main program, and one more thing, what is the name I have given here? It is a full adder. Okay. Now I have given a module ripple -8 adder. It is a user friendly name. You can use any name for it. Here I have named it as a ripple -8 adder. and then A, B, C and some new input variable I have chosen and the sum and carry of my outputs. And then in the basic full adder, this x, y, z are in 1 bit. Whereas in the ripple carry adder, it is going to be of an 8-bit wide. Therefore, I am naming it as an, I am declaring it as an array. Therefore, A is a variable 0 to 7. That is my array. Therefore, A0 to A7. My second input is B and that is also of 8-bit wide. Therefore, 0 to 7. Whereas the carry in, it is going to be 1 bit only. Therefore, input C in alone. C is a variable I have used. This input is a keyword. And then the output is also of 8 bits. Therefore, 0 to 7. And what is the name assigned to that sum? And then the another output is a carry and it is a 1 bit wide. Therefore, it is declared as set. And then in the full adder, in the circuit we have 3 intermediate variables T1, T2, T3. Whereas in the full adder, this ripple carry adder, at these stages you want to preserve the carry generated in the intermediate stages. Therefore, they are the temporary variables. So, how will you store the temporary variables? By means of the term wire. And what is the length of it? Cn you need not to show, carry you need not to show. Therefore, in between you have 6 variables. Therefore, 7. Therefore, 0 to 6 I have used. Clear? Therefore, 0 to 6 and the name I have given as C. Okay. Now, this process is known as an instantiation. What is the name I have used in the basic module full adder? The same name only here we have to use. If you change the name, then the program will not work. The same name, whatever you used it, the same name has to be replicated here. Okay. And then, like our previous thing, when you use the 2 XOR gates, what we used, we gave a name G1, G2 like this. Similarly, here I am going to use totally 8 times this full adder. Therefore, full adder FA1. When you consider this FA1, what are my inputs? A of 0 and B of 0 are input and the Cn is an input. These 3 are my inputs. And what are my outputs? Sum of 0 and C of 0 are my output. There should not be any swapping between the input and output variables. Okay. And then full adder to A of 1, B of 1. And what is my third input? The C of 0. That is the output of the previous is given here. And the sum of 1 and C of 1 are going to be our output. So likewise, this 8 adder, this full adder is instantiated 8 times in this thing. So this is the end module. Therefore, in the main module, when you have a hierarchy design like this, so in the main module, this basic module can be called many times. So this is the program. Okay. Once the program is done, now this project has to be created. Okay. The project has to be created. So Xilinx is one of the platform we have. This Xilinx is an ISC, that is Integrated Simulation or Synthesis Environment. It has a provision for creating a project and writing a program. This is the test mode. It will be in the editor mode. This program will be typed, and it has a provision for compiling it and producing the simulation. Okay. So after doing the simulation, that is in the another video about the execution of this Verilog module using a Xilinx platform. Okay, the Xilinx is a platform used to create and execute the program. Okay. Now, what we see at the output of the Xilinx? The Xilinx will produce the 2 output inputs. So, we will verify whether the circuit is created correctly. That is referred as an RTL, Register Transfer Level. That I will explain in the next one. This is referred as an RTL, Register Transfer Level. So, it describes what are the inputs are there and what are the outputs associated there. So, it is a high level abstraction level of the circuit. Within this, it looks like an IC, right? So, within this IC, you will have all the circuits we used in the circuit. Okay. Once this is done. Now, we want to verify whether the program written is working correctly for this logic. Whether if I give 2 zeros, whether it produces 0. When I give 2 ones, it is producing 1 0 like this, I want to check. Therefore, for that, the Xilinx have a provision that is referred as test bench waveform. That is a visual representation. Test bench waveform is a visual representation of the all possible inputs and output. This is a sample test bench waveform for my ripple carry adder. So as I told you, so we have, so here it is a simulated output, and what is the name of this waveform? Test bench waveform. So these are the 2 inputs, 0 to 7 and then Cin, and these are my 2 outputs. Okay. the inputs is like this, and when the other input is this one, so when I add these two together, 1 plus 1 is 0, therefore 0 is here, and 1 is carry generated, therefore this 1 added here, and that is generated by carry, that is my output. So that is described in the this one sum output. Whereas in the carry, at the 8th full adder doesn't generate any carry, therefore the carry output is 0. So this is known as our test bench waveform. In that you can see that this is a 0 nanosecond, 200 nanosecond. These values you can zoom it and zoom out, and you can see the result in the Xilinx platform.